I am now officially an old person because I'm here to talk to you about something that happened 25 years ago, and I've moved to history mode. So tomorrow I get to tell you about the future. Now I'm going to tell you about the past. So Northridge, this is just a plot of the Northridge earthquake. So you've got the rupture zone here. This isn't going to work. And then a lot of ground motion recordings. Most of the ground motion recordings are to the southeast there in the basins where we have structures and we put recordings. But there were recordings up in the mountains as well. So this was a big step forward for us. If you look at the data set that we had before Northridge, which was the blue, and then the Northridge earthquake, there is the red ones. We added a lot of recordings, sort of in this 6 to 50 kilometer range, and then there were the orange ones are some of the aftershocks from Northridge. The key here, though, is that this had some other features that were different for us, and I'll talk about the things that changed ground motion models. So if you go back to the 90s, ground motion models were very simple. You could program them up on a spreadsheet in 10 or 15 minutes. There was maybe 7 parameters in them, and they were very easy to do. That's not the case anymore. I don't even have students try to program up the new models because it's almost hopeless. But the key things we started with is here. This was a blind fault. Okay, and we had a buried rupture, and we didn't really know how to deal with that in the ground motion models. They had no parameter for that. They had magnitude and distance, and they had a style of faulting, whether it was reverse or strike slip, and they would also have a soil category, right? So we put things into classes of deep soils, and we put them into soft soil, which we didn't deal with, and everything else we called rock. Okay, so you need to keep that sort of in mind as to what we were doing. Other key things that happened were hanging wall effects. We didn't have these at all in our ground motion models. This turned out to be a huge limitation of what was there before. Also, we started to see large variations in the ground motion of what we thought were short distances. Stations a few kilometers apart are completely different in their ground motion amplitude. Even when they started to look at aftershock recordings spaced maybe 10 to 100 meters apart, and again, the ground motions were very different. Then we went to as well nonlinear side effects were beginning to be brought into the ground motion models, and the factors that we use after Northridge are very different. And then there's we're getting velocity pulses in these data. We have basin effects, and I'll talk a little bit about vertical ground motions. The last 3 there I'm not going to talk as much about, so it'll be a higher level. So if you went to Northridge and you said, what do we do first thing in those days? We plot up the peak acceleration versus distance, and we compare our curves to them, and you'd say, all right, on average, these things were 50% higher than what our model said it should be. So why is that? And so we go, well, it's a buried fault. We haven't had those before. Is that was the cause? Or was it because it was actually on a blind fault that doesn't reach to the surface? So the idea being there's higher stress drops from those types of earthquakes. Or the other parameter we had in our models to tweak was a style of faulting factor. That is reverse earthquakes stronger compared to strike slip than we had thought in the past. Okay, so then when we start to look at what's happening now, our models that we use now, almost all of them will include some sort of depth scaling. They scale either on the top of the rupture or the hypocentral depth. 2 of the NGA West 2 models don't have depth scaling terms in them. There is, however, a trade-off between the depth scaling and the style of faulting terms. And that's because reverse earthquakes tend to be deeper than strike slip earthquakes. So now I could model these effects in either way. I could shove them all into a style of faulting term, or I can put them into a depth term. If you look at how these models look like now, a depth scaling term, this is typical of what we use. This is how the earthquake term would increase as you get to deeper and deeper ruptures. The Northridge event is a red circle or square put on there, so it's an above average earthquake. In our current models, we'd only account for about half of that above average ground motion due to the depth, and the other half would be something else, okay, sort of a random behavior here. But as we get deeper and deeper earthquakes, we get bigger factors. So these factors are 0.7 on this scale here is a factor of 2 in ground motion. So we're going to start to get big differences in how the ground motion scale. The other thing about this is once we start to say earthquakes that are deeper or more energetic, we get to a problem or an issue that putting the rupture at the closest point to your site doesn't always lead to the largest ground motions. All right, because now in this simple case here, up here on the top, I have a vertical fault, and I'm going to put a magnitude 6.5 earthquake on there. If I put it all the way to the surface, the closest point to the site there, and calculate the ground motions, that's the blue curve on the right-hand side. And on the bottom here, if I take that rupture and push it down, it's a little bit further away, but it's deeper, my ground motions go up. So now your deterministic analysis gets a little more complicated because closer isn't always larger. All right, so in a probabilistic analysis, this is easy. The computer will do all that stuff for you. We now have to pay a little bit more attention to when we do deterministic studies. The biggest change really from the ground motion models due to Northridge was the hanging wall effect. Okay, and so this is just a sketch here. If I have a rupture shown by the solid line there, this is in cross section of a fault, a dipping fault. If I had two stations here, one on the left and one on the right, they're the same distance away from the rupture and as measured as closest distance, but the one on the hanging wall side on the right is closer to a lot more of the rupture than the one on the left. So just for a purely geometrical reason, we have a large increase in the ground motions on the right-hand side compared to the left-hand side at the same distance. Okay? Those factors get large. This is the data that we had in Northridge. So this was the first time we had this kind of data to work with, where we had, that's the rupture shown there. The hanging wall side is on the bottom. The footwall side is on the left. And we actually had recordings on both the footwall and the hanging wall side close in. That hasn't been the case in the past. So we didn't have the data to see what's going on. Right now, we have still only a handful of earthquakes with the data on both the footwall and the hanging wall. And there's really 4 of them that are useful at this point. So we're still at the point where this is an important factor for us. Using the data that was available from Northridge, what's shown on the x-axis is the rupture distance, but keeping track of it whether you're on the footwall side, which is negative, or on the hanging wall side, which is positive. And the circles there are the residuals. That's the misfit of a model that was fit to Northridge data compared to the observation. And on the right-hand side, they tend to be positive, right? But there's not a whole lot there. There's a lot of scatter. We went ahead and said we can draw a line through those points, okay? So we did that. That corresponds to about a 50% increase in the ground motion when you're over the hanging wall side. This was all there was to work with at the time. Okay, we were data poor, and we make models and charge forward. This model has held up remarkably well. Okay, actually, if I was to repeat this calculation today, that 0.4 natural log units, about a 50% increase, still is about what we get today with our current models. Okay. If you do this and apply it into your ground motion model, we came up with these now attenuation relations. The black curve would be a typical model that we would make, and the dash curve is how we increase it if you're sitting on the hanging wall side. Okay. So we still have not a lot of data, okay? And so these are all the earthquakes we had through NJA West 2 that had some recordings close in, either within 15 kilometers, on both, and we're looking at the hanging wall and the footwall side. So we need at least one on each side. But you can see most of those numbers on the right hand. So the third column over here is how many are at a joint abort distance of 0. That means they're sitting right on top of the rupture. Okay, and there's only a couple of earthquakes, about 4 of them, that's got more than one recording over the top of the rupture. The 2 main earthquakes that have data for us are Chi-Chi and Northridge, and then we go to Wenchuan and L'Aquila to try to get something to work with. That's all there is. Okay, so to help us out, we have to do, so if we plot the data from these, on the bottom here is the cross-section of the fault, and on the top are residuals again, and you can see if they're at 0, then we have no effect. When we're over the hanging wall, we only have a few recordings, but they tend to be high. Okay? If you're basing all this on statistical significance, you wouldn't do anything with this. This is 4 data points out of 10,000 that might be in your model. But we're not trying to build models based on statistical significance. We're trying to build models to capture a physical behavior that's important. Okay, so now the question is, does this physical behavior make sense? But we see an increase here for Chi-Chi on the left, Northridge on the right, and the other couple earthquakes, these are other 2 good ones. L'Aquila, not a lot to work with on the left, and then Wenchuan on the right. Okay, so, but they all tend to show an increase there. What gives us confidence in this is not that we're fitting 10 data points and trying to get a number, is that we start to now run numerical simulations where we can run thousands of realizations of these earthquakes and look at what the behavior is expected to be. So these are finite fault simulations that are run. Each gray point there is a simulation calculation. The black line is what you would get if you had no hanging wall effects. The ground motion is the same on the footwall or the hanging wall. Most of our data are on footwall, close in. You tend to put your cities and your locations of stations on the flat part, right? And you don't stick them up in the mountains, so we have a lot more data there. So our ground motion models tend to be footwall-based models, and now we're going to look at increasing them. So the key is there's a big scatter in any individual point. If I only had 2 or 3 data points on the right-hand side, that's what we've been trying to fit, right? So we can't control or constrain the scaling really with distance very well, or with magnitude, or with dip of the earthquake and depth. All these things start to affect it. So we have to use numerical simulations to constrain all of that. So from that, we have magnitude scaling, dip scaling, depth to top scaling, and Rx is this is the distance perpendicular to strike. That you can now make a model that makes physical sense and is consistent with those data. As you start to put that model in, the ground motion models are no longer a simple 7 parameters that you can code up in a little bit. They're starting to get more complicated as we try to impose physical behavior into effectively polynomials, right? How many polynomials do you need to match this numerical simulation behavior? Another issue from Northridge was some big recordings, particularly Tarzana, one of our really large recordings. So we're up to about 5G spectral acceleration there in the middle of the period range. At the time, the black line was a median model we've been using, and the 84th percentile is the dashed line, and we're way above that, right? So this is a really big ground motion, and people spend a lot of time sort of looking at this one and trying to understand it. This is from Paul Spudich. There's several studies that were trying to look at this. He's looking over here on the right-hand side. TAR is Tarzana. Here's the rock, and it's going into the sediments there. And there's nearby stations V10 and then ENL. So these are a few kilometers apart. However, the differences in the ground motions are large. So if we look at these ground motions here, the plotted up seismograms, they don't look so different. The 3 verticals, the 3 east-west, and the 3 north-south. But to do that, he had to multiply V10 by 3 and ELN by 6 to make them look similar. Okay, so there's a huge increase in this compared to what you get a few kilometers away. They went further and looked at the Tarzana station, which is the black dot here, and it's on a little topographic feature. And then for aftershocks, they put out all of these stations shown by the open circles and started to see tremendous variability in the ground motion over tens to hundreds of meters. Okay, so they worked out seismological reasons for why this happens, what's happening in some detailed basin, shallow basin structure here, or geologic structure. You can find that out afterwards, but we don't know this ahead of time. right? If you're going to put a structure here, we wouldn't have known that this is going to be 3 times or 4 times higher than a typical site, okay? So our ground motion data sets are severely spatially aliased, right? We don't really sample what's out there. And we're at the mercy of whether we're sort of on highs or lows as we're going forward. So starting to find ways to bring in more dense samplings of data is even from smaller earthquakes will help us. Another issue for Northridge was basin effects. I'm not going to talk much about this. The seismology community spends a lot of time on now doing, taking these kinds of data, building 3D or 2D or 3D geologic crustal models, calculating the response using analytical wave propagation, and then comparing that to the data. So then there's large effects that they can say a particular station is going to be high for an earthquake in this one spot. If the earthquake is in a different spot, you can get a very different distribution of the highs and lows. So it's complicated. When we build this into empirical models, we had to simplify that tremendously, okay? And we simplified it to simple scale factors based on basin depth. That was the thing that at least a first order could distinguish between a soil site that is a shallow soil site or a soil site that's in a deep alluvial basin. This scaling though, scaling with Z 1.0 or 2.5, so the depth to 1 or kilometer per second or 2.5 kilometers per second, varies by region. This depends on basically the velocity structure. So you can't take these models and really move them around. The newer ground motion models are developing region by region basin scaling terms. And that's sort of the complexity that's going to start to happen in all these models, is recognizing this isn't all simple ergodic model, but we're going to have to do something more complicated. So after Northridge, what have we been doing? We've been running or using 3D numerical simulations for basins. However, there's an issue of how do you tie simulations together with an empirical model? And the problem we face is that our empirical models already have an average basin effect in them. They're not 1D models. They don't represent ground motion in a 1D model. They represent the average of a 3D Earth. So the 3D effects are correlated to the shear wave velocity models that we have. Right? So we already have basin effects implicitly on average built into our VS30 scaling in the ground motion models. So to avoid double counting those pieces, we have to use an average reference as an average depth of the basin for each VS30 that is in our generic model, and then look at deviations from that. We can't take 3D simulations divided by a 1D simulation and use those numbers. Okay, that's what had first happened when we started to have simulations done, and you looked at it and go, these don't fit together. So now we have methods to try to make this all sort of fit in a reasonable way. So nonlinear site response, I'll talk just briefly about, but after the Loma Prieta earthquake, we had a lot of data on soil sites, and were able to really evaluate nonlinear effects empirically, really with a good data set for the first time. And those site factors got built into the building code. After Northridge, when they looked at the site response, it wasn't consistent with that model post Loma Prieta. And there was a project called Resolution of Site Response Issues in the Northridge Earthquake, so ROSRINE was the acronym, and basically found that the soils in this region were more linear in their behavior than the soils in the Bay Area region from Loma Prieta. So that changed the way we started modeling things. This isn't my field, but those of you geotechs will recognize geology max curves. The top ones are curves that were based on Loma Prieta. On the bottom ones, these are all cohesionless soil curves based on Northridge. The bottom ones are more linear. If you look at the curves, they're higher up than what the curves are on geology max, don't fall as fast. So we have more linear models. These are now more consistent with the empirical data around the world. So this is actually a better average nonlinear behavior than we have for the models used in the Bay Area. Okay, last peak velocities. We got large peak velocities in Northridge, in close 100 centimeters per second in multiple recordings. If we look at data, this is just actually pulled out of the pure Groundmotion database, so you can make these same plots. At Rinaldi receiving station, we have a nice velocity pulse, right? 140 centimeters per second, so a very big velocity packed in a small amount of time with a really simple waveform. So this is one of the classic records that we end up using for trying to find a near-fault pulse recording. Verticals, right after the earthquake, there was reports coming out, we have several recordings over 1G vertical, and what does that mean? And there was talk about, was damage here related to the verticals instead of related to the horizontals, because the verticals were high. Really, they're high, the verticals are large, but the horizontals are larger. Okay, and so this isn't a case of large verticals, it's a case of large horizontals. If we look at the horizontal to vertical ratio from Northridge, this is data within 15 kilometers. You look at this, and this is a typical looking V over H ratio shape. It comes in at peaks just below 0.1 second, it has a trough, and then comes across. So it's not verticals were big or unusual, you just had a large horizontal which they went with. So what are we trying to deal with going forward? Depth scaling. That's now part of ground motion models, and I think that's here to stay. That will tie more with seismology as they start to look at stress drops of earthquakes, and we can make this a more physical process. Hanging wall scaling is really important. It's a factor, up to a factor of 2 in the short period ground motions when you're close into faults. We tend to put our dams where we have topography, which is from faults, so they're almost always sitting on top of our hanging wall. Basin factors are now again becoming common. And nonlinear site factors here, we're using the nonlinear factors that are consistent with the Northridge soils, but that means our GMPE's factors are not consistent with what we're using in the Bay Area, right? We're using an average, we're not using a model that's optimized for the Bay Area. So again, the regional factors are closer to the Northridge earthquake. Okay, tomorrow I get to tell you something new as opposed to something old. All right, so thank you.